To comprehend our reality as a digitized simulation, a good understanding of numbers is necessary. As far as recorded history shows, the ancient Sumerians were the first to turn the symbol 1 into a token, and create systematic arithmetic with it. Their arithmetic was used only with the number 1. Therefore, when writing down the numbers for 100, they would have to write 100 lines of ones. It was the ancient Egyptians, however, who gave identity and personality to their numbered symbols when gathering large groups of ones. They had symbols for different groupings of ones, ranging in the thousands and even millions. The Egyptians were the first also to transfer the number 1 from counting things to measuring things. Later on in Greece, while other Greek philosophers were claiming everything in the physical universe was made of the 4 elements, the Greek philosopher Pythagoras was teaching his students everything was really made of numbers. He believed the information expressed through number symbols was the essence of all physical existence. Also, as I stated in part 1 of this documentary, Pythagoras taught us the beauty of music was based on relating integers of numbers. Thousands of years later, the German mathematician of the 17th century, Gottfried Leibniz said, "Music is the pleasure the human mind experiences from counting, without being aware that it is counting." But, concerning numbers, Pythagoras couldn't perceive of numbers unless they represented actual things. This is to say, the number 1 wasn't something unless it stood for something, like 1 flower, 1 brick, 1 step, 1 horse. But the mathematicians who came about after Pythagoras broke free of these constraints. Probably the greatest mathematician of the ancient world was Archimedes of Syracuse. It was he who would take the first steps towards abstract mathematics, the kind of mathematics physicists perform today. This is to say, theoretical mathematics. He took arithmetic a step forward by creating for himself elaborate math games where he could calculate things like, how many grains of sand would it take to fill the world? He should be considered the first theoretical mathematician of the classical Greek age. When Rome came to power, theoretical mathematics was stifled. The Romans were more concerned about power and possession than theoretical mathematics. Numbers in Rome were used for counting things like how many soldiers do I have in my possession, how many archers do I have, how many acres of land, etc., etc. Even the number symbols created by Rome took the world back to the Stone Age. And, as Roman power spread throughout the Old World, so did its numeral system. The Roman numeral system was good for counting things, but notoriously terrible for calculating anything. For instance, if you were to write 1 billion on a piece of paper using our modern numbering system, it would take about 7 seconds. Using the old Roman numerals would take well over 10 minutes. For centuries, the Romans held most of the world back with their Roman numbers. I guess this is why, unlike the mathematicians of the classical Greek age, not a single Roman mathematician is celebrated today. Unlike those in Rome, the Indians of India devised a numbering system that could cope with vast numbers that would otherwise overwhelm the human mind in calculations. It seemed India was less concerned about military organization and more concerned with enlightenment. While the Romans were dumbing down the world with their Roman numerals, India was bringing forth new numbers through theoretical mathematics on stupendously huge scales. But truly, the game changer for the world of numbers and mathematics was India's development of a different number symbol for every number unit, ranging from 1 to 9. We call these symbols Arabic numbers. For the first time in history, humanity saw the numbers, not only as separate individual entities, but also as a collective group. Then years later, the people of India would change the game again. After the creation of Arabic numbers, someone in India introduced a new symbol to Arabic numbers that would revolutionize the entire world, since the ancient Sumerians' creation of systematic arithmetic. Yes, for the first time in human history, someone had made nothing into an actual number symbol that could be calculated. This new number symbol 0 would seem to be not a big deal on its own, but when connected with the other 9 counting symbols, the Indians could now make and calculate numbers infinitely large and infinitely small. This 10-base Arabic counting system enabled Indian science to storm ahead tremendously. For instance, Indian astronomers were centuries ahead of the Christian worlds. Indian scientists had already worked out the Earth spins on its axis and moves around the Sun, 1,000 years before the European mathematician Nicolaus Copernicus. Indian scientists were also the first in recorded history to calculate the diameter of the globe. And they were only less than 1% off the correct calculation. All of this was possible because of their newly created 10-base numeral system. There was an Italian mathematician named Leonardo Fibonacci, who found a great fascination with India's 10-base counting system. He took the Indian numbering system to Europe in his Book of Calculations, which resulted in the 10-base numbering system taking over the Western world. In fact, this new numbering system became the vocabulary for modern-day banking as we know it. But although the Arabic 10-base numbering system that left India was a smash success with the Western world, calculating large amounts of numbers through it still found some problems, because the 10-base system allowed room for much human error. Some 400 years later, in the 17th century, it was the mathematician and philosopher, Gottfried Leibniz, who was determined to rid humanity of human error when calculating long strands of numbers. He was bent on doing this by inventing a calculating machine. But once Gottfried finally built his 10-base calculating machine, it dawned on him that the numbers 0 and 1 was all that was really needed to eliminate human error and achieve any mathematical dream. So, he got rid of all the other numbers and developed a number system just using zeros and ones. Today we call it the binary numbering system. A machine driven by his binary system didn't come to fruition until 1938 with the Z1, the first freely programmable computer in the world which used Boolean logic and binary floating point numbers. But the Z1 computer wasn't totally reliable. Therefore, a more efficient computer was developed in the years 1943 to 1945 to help in the cryptanalysis of the Lorenz cipher. This computer was named Colossus. Colossus was Gottfried Leibniz's dream made real. With Colossus, Gottfried Leibniz's ones and zeros binary numbering system would finally come into its element as electrical currents. Electrical current of the number 1 equating to electrical current on. An electrical current of the number 0 equating to electrical current off. And this technology has changed our world forever. Through binary, a machine could keep track of large strands of numbers, something humans find difficult to do. Gottfried Leibniz's binary counting system in computers would make calculated mistakes a thing of the past in our digital age. In the world of computer computation, a data system is a term used to refer to an organized collection of symbols like zeros and ones, as well as processes that may be used to operate on such symbols, such as a binary processing system. In a nutshell, any organized collection of symbols and symbol manipulating operations is what we term a data system. When we think of a data system, we tend to only think about computers. But the entire universe, and everything in it, is of a digital persuasion working through a data system very much like our personal computers with their zeros and ones. This will be shown as this documentary unfolds. The word digital simply means of, or relating to information that is stored in the form of the numbers 0 and 1. Oxford Dictionary defines the word digital this way. Expressed as series of the digits 0 and 1. Typically represented by values of a physical quantity such as voltage or magnetic polarization. To understand how a data system functions in a computer, it is important to understand how a computer bit works. The bit, short for binary digit, a term first used in 1946 by John Tukey, is the smallest unit of information in a machine. I give reference to the bit because, at the end of the day, we are all machines. Every living creature, every human cell, even the universe at large is a working machine of wonder. It was Gottfried Leibniz, in his attempts to understand the mechanisms that make the universe function, who believed the world we see around us was a vast machine designed by a powerful mind. And if you could understand how machines worked, Gottfried believed you could understand how the universe works. A machine is an assemblage of parts that transmit forces, motion, and energy one to another in a predetermined manner. Machine, Merriam-Webster Dictionary. The definition above gives reference to the machine, while describing our universe very well also. In reference to today's computerized machines and the bits they use to function, the viewer should understand the single bit can hold only one of two values, 0 or 1. Therefore, the power of the bit lay in this universality. Any system that has two states like a coin with heads and tails can carry one bit of information. Therefore, the bit is the common language for communicating information within two state systems. The bit is the smallest quantity of information available in a two-state system. In binary, every bit is either 0 or 1. In understanding how our universe works as a simulation program, it is highly significant to grasp hold of the idea of the bit as being the smallest unit of information, which there is sufficient discrimination to communicate anything at all. Anything, text, pictures, sound, etc., can be turned into bits and transmitted by any system capable of being in two states. In reference to computers and data systems, I'd like for us to now take a look at a game called Conway's Game of Life, a video game where cells merge together to form longer, more complex cell structures. The game shows us, through the binary information of computer bits within a data system, more meaningful information, that is, longer strands of information, can be created by combining consecutive bits into larger units termed bytes. In computer science, 8 consecutive bits of information equal 1 byte of information. The more bits and bytes used, the more complex the information can become. In a computer data system, the bit-byte growth process is a building of information into more multifaceted information, which works along the same lines as fundamental biological life forms that combine to form longer strands of chemical, biological life forms. If you are wondering how chemical elements, which is to say atoms, become biological organisms, which is to say cells, the bringing forth of biology out of chemistry is brought forth through number sequences, binary code, as you shall see with the unfolding of this documentary. As mentioned above, it is all a mere building of information. But the chemical to biological outgrowth process is much more complex than the mere combining binary bits into bytes as in a computer. With biology, it is not only sequence of numbers, but also a sequence of correct temperature and time. In 1970, a brilliant mathematician named John Conway devised a game called the Game of Life, a two-state cellular automation that shows how our universe could have come about by a set of simple rules founded on a two-state system. His Game of Life is a zero-player game with an evolution that is determined by its initial state, requiring no further input. The mode of the game is to create an initial configuration and then watch it evolve on its own through the simple basic rules, or information first imputed. His computer-simulated game consists of a regular grid of empty space extending infinitely in all directions, as shown here. Every cell on the grid, which is symbolized by a square, sits in a state of off or on, that is, 0 or 1. Typically, the rule for updating the state of cells is the same for every cell. These rules are applied to the whole grid simultaneously, in the initial state of the game, and do not change over time. Then, according to fixed rules, a new generation of cells is created. For every cell, a set of cells called its neighborhood is defined relative to the specified cell. The fixed rules determine the new state of each cell in terms of the current state of those cells and the state of the cells in its neighborhood. Each cell on the grid can be lit up, which equals alive, on, or the number 1. When the cell is dark, this equates to dead, off, or the number 0. Whether a cell is dead or alive depends on the other 8 cells that surround it. For example, if a living cell has no living cells around it, the rule says it will die of loneliness. Cells can also die of overcrowding. A dead cell surrounded by 3 living cells causes the dead cell to come to life. Be born. Once you set the initial laws for the living cells, and then let the simulation run, these simple laws determine what happens on the grid in the future. The results are astounding. As Conway's Game of Life program progresses, shapes appear and disappear spontaneously. Collections of shapes move across the grid, bouncing off one another. The objects that are brought forth began to interact like species. Some shapes can even reproduce just as life does in our reality. My point in bringing up Conway's Game of Life is this: these complex properties emerge from simple laws that contain no concepts, and are believed by some in the science community to be how the physical universe began. Even the late great Sir Isaac Newton believed everything we see follow a few simple rules, which when added together build up to explain the complicated physical interactions all around us. Our universe operating off a binary coded system of zeros and ones, offs and ons, would explain why we live in a dual reality of negative-positive, found in chemistry, male-female, found in biology, and good-evil, found in psychology. A very outstanding discovery about transferring information was made in the early part of the 19th century. This discovery came about through Joseph Jacquard's invention of the loom, a device used to weave cloth. First demonstrated in 1801 with the use of punch cards, Jacquard's loom simplified the process of manufacturing textiles with complex patterns. In his invention it was found, information can be transformed very easily from one state to another. With his loom, any design you could think up could be broken down and made into a series of punch cards, and then could be woven by the loom. In this process, information was being transferred from pictures to the punch cards, and then to the actual fabrics. The punched cards held within it the essence of the design the loom would weave, recreating the pattern in fabrics. Jacquard's loom revealed the power of abstracting information. It showed, you could take the essence of something, abstract the vital information, and then represent it in another way or form. Just as binary numbers had revealed two symbols could be used to capture information, his loom had shown that just with two symbols, holes and blank spaces, a representation of zeros and ones, it was possible to capture the information in any picture imaginable. Here's a portrait of Jacquard that has been woven in silk. It is spectacularly detailed with hundreds of thousands of stitches. And yet, all the information you need to capture this lifelike image can be stored in a series of punched cards, 24,000 of them to be precise. This picture is a fantastic example of a really far-reaching idea that the simplest of systems, in this case cards with a series of holes punched in them, can capture the essence of something much more complex. Imagine, if 24,000 punch cards can create an image like this, what would happen if you had 24 million? Or 24 trillion cards? What new types of complex information might be able to be captured and represented? Although it was the German mathematician and philosopher, Gottfried Leibniz, who introduced the binary numeric system to the world in 1689, it was the mathematician and electrical engineer, Claude Shannon, who took Leibniz's binary numeric system a huge step forward. Shannon's groundbreaking 1948 paper, A Mathematical Theory of Communication, showed the world there was a common commodity associated with all messages transmitted through radio, telephone, television, satellite, etc., etc., and this common commodity was information. Like Jacquard's loom, which showed information could be transferred from punch cards to pictures, Claude Shannon's paper showed us, any kind of information could be represented digitally in binary form. In other words, any kind of information could be broken down into sequences of bits of information. Claude Shannon's ideas revolutionized the way engineers and scientists thought about communications, galvanizing researchers and spawning a new school of thought called information theory. Information theory is the mathematical study of the coding of information in the form of sequences of symbols, impulses, etc., and of how rapidly such information can be transmitted, for example, through computer circuits or telecommunications channels. Information theory, Google definition. Shannon was the first to show us, by using a fundamental element, information can be quantified, no matter the form the information came in. He saw the binary digit as the fundamental element in communication, and thus postulated, information could be broken down into encoded sequences of bits, meaning zeros and ones, then transmitted across telephone wires and then decoded at the other end with no loss in quality. Some 40 years after his paper was published, Scientific American and other publications labeled Claude Shannon's paper, the Magna Carta of the Information Age. Today, we use the same bit structure binary concept in our computer graphics. Computer graphics are often classified by the number of bits they can process at one given time. In computer graphics, the graphics are often described by the number of bits used to represent each dot or pixel on the screen. In his book, Staradigm, Pao L. Chang paints out the picture of binary usage in computer graphics this way. When we paint a picture using computer software, the core state of the colors and shapes in the picture are basically made of ones and zeros. We do not see our picture as ones and zeros, because the central processing unit, CPU, and its counterparts process the binary codes as colors and shapes. The greatest thing about binary codes is that there are no limits to their combinations. Staradigm, Pao L. Chang. When you look at your computer's two-dimensional, 2D, monitor and see a three-dimensional, 3D, image in motion, is it not the manipulation of binary code that bring forth the 3D imagery you see on your 2D screen? What you are witnessing on your monitor is a second-hand production, produced by written script, binary code, zeros and ones. The reason you don't see the actual binary code on your monitor is because the computer's central processing unit, its CPU, process the binary codes as colors, shapes and etc. It is a mere bit-byte binary coding of numbers that carry light and geometric information to your 2D computer monitor, manifesting its display as a 3D simulation. The 3D imagery upon a 2D display monitor is achieved through what is termed in computer science, voxels, which work like 3D pixels. Note, a regular pixel, something you would find in a photograph, defines a point in two-dimensional space on a two-dimensional surface with its x and y coordinates. A voxel, however, is a unit of graphic information that defines a point in three-dimensional space on a two-dimensional surface. Since a pixel, picture element, defines points in two-dimensional space with x and y coordinates, a third z coordinate is needed to create a voxel. In the artificial 3D space on a computer monitor, each of the coordinates is defined in terms of its position, color, and density. With this information, and 3D rendering software, a three-dimensional view from various angles of an image can easily be obtained and viewed on your 2D computer monitor. Medical practitioners and researchers are now using images defined by voxels in 3D software to view X-rays, cathode tube scans, and magnetic resonance imaging (MRI) scans from different angles, effectively to see the inside of the body from outside. Our information age, 80 years in the making, has taught us many things about life on the supermicroscopic scale, transforming many of the things we thought we knew about our world and universe. With the invention of the computer, the internet and its evolution into mediums we all have access to daily, our world has become an information melting pot. Today we live in the most prosperous information age humanity has ever experienced. For instance, the average high school student today knows more about the universe at large than scholars just a few centuries ago. Information and ways of acquiring more of it has exploded in these times of ours. But still, I imagine thousands of years from now, humanity will look back at our first century of computing with adolescent eyes, and see a world trapped behind a screen, people interacting with 2D technology on a monitor. Our descendants may view our technological age as primitive as we view Neanderthals and their cave drawings. The technological age we are currently in is still in its infancy stage with much room to grow. Today's software companies are moving us forward by experimenting with the digital powers found trapped behind our 2D monitors. They are removing the monitor altogether, and thus, freeing us from the 2D confines of traditional computing, bringing forth a world devoid of 2D technology. To break down the thin liquid crystal wall between technology and humanity, Microsoft is one of the companies that is leading the way in our next step in technological evolution, with their HoloLens mixed reality smart glasses. Their holographic technology allows us to interact with 3D simulation reality, without being limited inside a 2D world of monitors and pixelated devices. This new unlocked screen approach to computer technology is showing the world just how similar our computer simulations are to our actual reality. When we observe physical reality close enough, like the voxels on a computer monitor with all their three-dimensional information, our view into reality dissolve into individual little chunks of information. At first glance of reality, we see what seems to be a smooth infinite continuum. But a much closer look shows our reality breaking down into quantum mechanics. The unaided eye can see the pot of water sitting on a stove, but is unable to see the trillions of tiny water molecules comprising the pot of water. On the quantum level, the pot of water is comprised of super microscopic chunks of information. All the physicalities of our universe are made up of these super microscopic chunks of information. But like the computer monitor and its pixelated chunks of information, the microscopic information that makes up the entire physical universe is not readily seen on the surface of things. This information can only be seen when you start to probe deep into physical reality. Our current understanding of natural reality on the quantum level breaks down at what is known as the Planck scale, an energy measurement scaled around 1.22 times 1019 GeV. It is a sort of pixel scale of our familiar reality. Planck's law is defined by Google as a law forming the basis of quantum theory, which states that electromagnetic radiation from heated bodies is not emitted as a continuous flow, but is made up of discrete units, or quanta chunks of energy, the size of which involve a fundamental physical constant, Planck's constant. Planck's law, Google definition. It was discovered in the early 20th century by Albert Einstein and Max Planck, through what is termed in history the ultraviolet catastrophe and the photoelectric effect, that energy is not emitted in our universe as a continuous flow, as had been taught for the prior centuries, but rather is made up of discrete units of quantized energy. This is to say, our experience with what seems to be a flow of energy throughout our reality is really little microscopic voxelated chunks of energy. Today, 100 years after Planck and Einstein, it is believed that space and even time may not be an infinite continuum, but rather exist at their most fundamental levels as supermicroscopic chunks of information quantized down to the Planck scale, the shortest possible length in the universe. The Planck length is so small that there are more Planck volumes inside a cubic meter than there are cubic meters in the known universe. Be on the lookout for part 3 of this documentary series, as we probe even deeper into reality, with the notion of humanity living in a simulation. Be sure to like and subscribe, and thanks for watching.
Have you ever questioned the reality of the world around you? Are we living in a computer simulation? Digital reality. Our Universe is a Simulation by Michael Cage. In this thought-provoking book, author Michael Cage explores the concept of digital reality and the possibility that our entire existence is just a simulation. With a blend of philosophy, science, and technology, digital reality takes you on a journey through the history of virtual reality and computer simulations and explores the implications of living in a digital world. Join the discussion and challenge your perceptions of reality. Get your copy of Digital Reality today. Available now at all major bookstores and online retailers.